Hello, everyone, and welcome to today's broadcast, Accessories and Techniques for FT-IR Sample Analysis. It is presented by Richard Larsen, Ph.D., a Senior Product Specialist at Spectral Consulting. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I'd like to remind everyone this event is interactive. We encourage you to participate by submitting as many questions as you want anytime you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions into the drop-down box that appears on the screen. Our speaker will respond to your questions via email. If you have trouble seeing or hearing the presentation, please click on the Ask a Question box to let us know that you're having a problem. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located in the top right corner of the presentation window and follow the process to obtain your credits. Please join me in welcoming Dr. Larsen. I will now turn the presentation over to him.
Thank you, Judy, and thank the audience for being able to attend today. I greatly appreciate it. The discussion today is basically how to get more out of your instrumentation. And there's a lot of different wavelengths that affect a molecule. So all molecules absorb energy in a lot of different ways. Different wavelengths of light each contribute to information about the molecule in terms of structure, composition, or the electronic configuration of the molecule. Infrared, or mid-infrared, as it's termed, is a very narrow range of that wavelength stream. And you can see the rainbow of colors up on the top here. But you're talking about a very narrow range from about 2,500 nanometers, which is 4,000 wave numbers, to 25,000 nanometers, which is 400 wave numbers. The reciprocal centimeter, or wave number notation, is specifically for this particular region of the spectrum. And it was done so that you worked with whole numbers. You discussed whole numbers instead of 2,500, 0.653, or things like that. Or the numbers got extremely large, like 24,561, something like that. So it's just a convenience for us in the industry to use those wavelength values. So in infrared spectroscopy, or FT-IR, incident white light interacts with all the vibrational modes of the molecule as it continues to vibrate. All those little atoms that are attached by molecular bonds are moving in different directions, and they absorb energy from the source. And on the other side of the sample, what we get is missing lines, basically. The molecule has absorbed some of that light. And if we compare the light before the molecule and after the molecule, we can actually see a difference in the spectrum. And what we see is an absorption spectrum that is characteristic for that particular molecule. So as the molecule vibrates, in this case, we're looking at a molecule of water where oxygen is the red atom in the center, and the two little hydrogen atoms are on either end. And it's continuously vibrating, moving in different directions. And when there's changes in that vibration, there's actually a very small change in the polarizability. The oxygen is slightly negative, the oxygens are slightly positive, the hydrogens are slightly positive, excuse me. And that polarizability changes a little bit as the molecule stretches and bends. And we need that interaction along with the light absorption to see the infrared spectrum, because what happens is there's an absorption process that occurs. And this is the energy levels in the quantum values, and we're looking at changes between the V0 and V1 levels, which is the vibrational modes. The larger excited states that we see up at the top has to do with the UV-Vis absorption, which we're not going to discuss in this presentation. So we're talking about these little energy gaps where the molecule's transitioning between the ground vibrational state and the first vibrational state, or in the overtone modes from V1 to V2. And sometimes we start off at V1 and go down to V0, and that's an emission mode. So we've talked about all the little things that do happen when we look at the vibrational modes associated with infrared absorption. So what we end up getting is we see that this little oxygen-hydrogen amalgam called the water, we have symmetric stretches, anti-symmetric stretches, and the bending modes. And when we look at that in the infrared spectrum, we see the OH stretches all mashed together here because they're so strong and they're so intense. And then the OH bends at another wavelength value. And this is very specific to water. So if we change one of the atoms in the hydrogen, from hydrogen to deuterium, the spectrum would change completely. There would be additional information because we have OH and OH stretching and OH bending, and OD stretching and OD bending. So there would be two more peaks that would be added to the spectrum. This information here is actually in overtone mode. So when we look at something that's a little bit more complex, like isopropyl alcohol or isopropanol, we see a lot more activity in the spectrum. So just like we saw in the previous spectrum, we have the OH stretch here right about 3,400, the CH and CH3 stretching modes that are right around 3,000, the CH and CH3 bending modes that are below 1,500 but above 1,000, and then the carbon-carbon and carbon-oxygen stretching modes, and the COH bend. And there's other bending modes that are involved in this as well for the carbon-carbon and carbon-oxygen. If we go to something like benzonitrile, we have more activity. And in this case, the benzene CH stretch, because they're all the same, we only get one peak instead of the multiple peaks that we saw for isopropanol. The carbon-nitrogen, the triple bond carbon-nitrogen stretch is all by itself out there about 2250. And that's the only thing that really gives a band in that area. We have the ring breathing modes, carbon-hydrogen bending, and carbon-carbon stretching, and carbon-carbon bends. So it's a fairly simple molecule, but there's a lot of activity because there's a lot of atoms in that particular molecule. So as I said before, every time we look at a molecule, we get different activity, different absorption modes or absorption peaks based on the different functional groups that are present in the molecule. And one thing to note is that if we have benzene ring CH stretches, they're generally above 3,000 wave numbers, and the aliphatic or straight chain CH stretches are below 3,000 wave numbers. There's another COC stretch right about 2250, same as that nitrile, the C triple bond N. And then we have the HOH bend, the amide 1 and 2 bands for proteins. Carbonyls are right around 1750. Benzene rings, we see some things there, and so on down the line. The idea is that as we become more accustomed to looking at our spectra, we start to recognize certain functional groups and say, yes, I have an alcohol, so I should see a very strong wide band above 3,000. And I have an amide band, and I should see some activity around 14 to 1,500. Those are the types of things that start to become implanted in your brain as you keep working with the spectra. Well, we're not going to go into complete interpretation today, but we're going to talk more about the capabilities of the infrared analysis method. So the biggest one is identification and quantitation of organic, solid, liquid, or gas samples. Infrared spectroscopy is one of the few techniques that can give me exact identification of a molecule, especially when I compare to a library of data. I can do analysis of powders, solids, gels, emulsions, pastes, pure liquids, solutions, pure and mixed gases. Infrared is used for research, methods development, quality control and quality assurance applications, among others. And samples can range in size from little fibers, only 20 microns in length, to atmospheric pollution studies involving fairly large areas. they set up cameras and detectors across a quarter-mile range to see if there's a gas plume that's going across a certain area. Just as an example of how we do very large pollution studies. Lots of different places that infrared is used. Pharmaceutical research, polymer analysis, environmental water quality analysis, QA and QC, biochemical and biomedical research, and the list goes on and on. And every day there's new discoveries that are made using infrared spectroscopy. Excuse me. Beer's law describes the ability to do an analysis of concentration because sample concentration is directly related to the infrared absorption intensity. So the capital A is the absorption intensity, the value of either peak height or peak area equal to the absorption coefficient for a specific infrared peak in a specific sample, the sample path length, how long or thick the sample is, and the concentration. Basically, the coefficients A and B fall out, so we have a direct correlation between capital A, the absorption intensity, versus the sample concentration. And what we do is we plot the concentration of the peak intensity or the peak area versus the absorption intensity, the peak intensity versus the concentration, and we develop a calibration curve like this, where we see that there's a fairly straight line that can be drawn through all the different points based on that peak height or peak area. So from that point forward, we could look at that particular molecule, whatever it is, and say, yes, I have 0.35 moles present at, because my absorption intensity is about 0.73. So a good infrared spectrum, what are the criteria? The spectrum baseline should be relatively flat. We don't want a lot of curvature or a slant going off one way or the other. The highest transmission point should be between 95 and 100% T. It can be a little bit lower. We certainly don't want it above 110% or 100% T, rather. There should be fairly little noise in the spectrum. Most FT-IR instruments, that's Fourier transform infrared, the most common instrument everybody works with, will obtain a sufficient signal-to-noise ratio, or SNR, within a minute of scanning the sample, anywhere from 16 to 64 scans, depending on the model and the configuration. The strongest band in the spectrum should be greater than 50% T, percent transmission, and should fall no lower than between 3 and 10% T, because then we're running into the problem of overabsorption, where we're going beyond the sensitivity of the detector. And the last comment there, sample preparation is the most important aspect of collecting a useful infrared spectrum. So here is a good FT-IR spectrum for a KBr pellet of ibuprofen. We have a flat level baseline at about 100%, good signal to noise ratio. Our peak maximum is right around 10%, not greater than 5%. And we got nice sharp peaks with no interferences anywhere in the spectrum. Good. So the first technique we're going to talk about is transmission sampling. Transmission analysis is the most common and most universal method for analyzing the solids, liquids, and gases that we're interested in. Transmission spectra have the highest sensitivity and best detection levels of all the infrared sampling methods. There's lots of different documented analytical methods, and in many cases, it is the only recognized analysis method. Transmission methods include KBr pellets, sample mulls, the use of liquid or salt cells, and thin films of liquid or polymer samples. And as a graphic to illustrate all this, we have the KBr pellet technique, where we mix KBr powder and a powdered sample and then form it into a little pellet. The thin film technique, where we place a very thin amount or a small amount of the sample onto a KBr plate, either dissolved in an organic solvent, let the solvent dry off, and create a thin film, or actually put another window on top of that, like this one, where we have a small amount of liquid trapped between the two windows. And then we also have a solution technique where we can put a solution or sample in a fixed path length cell and get an analysis doing it that way. The KBr Pellet is the most recognized method. I think everybody that's ever done undergraduate chemistry and organic class has done a KBr Pellet. At least I hope so. Because you learn a lot trying to do that. It's not the easiest method, but it gives you very good sensitivity. And once you've mastered the ability to make a KBr Pellet, everything else is much easier. So there's lots of USP and forensic analysis methods that utilize KBr Pellets for collection of spectra. There's lots of different ionic salts that can be used for this, such as sodium chloride, potassium chloride, or cesium iodide, but potassium bromide is preferred. These materials are very moisture sensitive, and you've got to move quickly, because if you've got a lot of humidity in the laboratory, they'll suck that humidity and moisture right out of the air and become wet. And it can be a challenge if you don't use the proper procedure. So one thing that can go wrong is if you don't collect your background spectrum through the blank pellet holder, you can get what's called vignetting, or restriction of the beam. And that can cause wave number shifts or incomplete compensation for the atmospheric water band. So when you see the bottom spectrum here in this figure, you see a lot of activity around up above 3,500, and again around 1,700. And then there's also some stuff occurring right around 2,250. That's because you're not getting good compensation for the water and CO2 that's naturally in the atmosphere. There's also some changes, excuse me, to the spectrum that affects the quality of the spectrum that you're getting. So when we look at the top spectrum, we ran the background with a 7mm blank, and we got a much better signal to noise ratio spectrum and much better quality of the spectrum by accounting for the compensation of the beam restriction. So here we incompletely ground the sample or did an improper pressing, and what we see is this severely sloping baseline. The baseline starts at about 60% T, goes down to almost zero, and we see this large slope associated with the spectrum. And that means that something is not quite right. And in this case, we've got way too much sample in the spectrum, in the pellet. And so we see the slope again, and we see that the bands are touching very near 0% transmission. And so we've overloaded the pellet, so to speak. We don't have clear, distinct peaks in the spectrum so that we can do a good identification of what that material is. We also see a lot of overtone bands here between 2,000 and 3,000 wave numbers. That's due to the intensity of the peaks down here in what's called the fingerprint region. So when we've pressed a good pellet, we get a good spectrum that looks just like this. Nice flat baseline again, peaks that are right around 10%, 15% T, nice sharps peaks, no interference peaks due to the water, the CO2. It's just a good spectrum overall. So Mull samples is another technique that can use your powders. Basically, it's a mixture of either Nujol mineral oil or Fluorolube, which is another good lube material, and a powdered sample. The powder is mixed with the mulling oil, and then the mixture placed between the two salt windows to collect the spectrum. Generally, mulls are used for samples that can exchange ionic components with the KBr salt. It is also a simple and inexpensive method for sample analysis. We need something quick. Nujol and Fluorolube oils also have an infrared spectrum and must be subtracted from the Mull spectrum. So basically what we do is we collect the spectrum of the oil without the sample and use it as a reference to do a subtraction after all the spectra are collected. Here's a case where we collected the Nujol oil separately, and we have our caffeine in the Nujol, and we did the subtraction, and we just want to make sure we mark the peaks where the Nujol was subtracted to make sure there's no possible interference with the caffeine spectrum. Other sampling techniques include liquids. So we use liquid cells with either water-soluble or water-insoluble windows. Water-soluble windows of potassium bromide, sodium chloride, or cesium iodide are very moisture sensitive. Materials should be handled carefully as they will quickly absorb water or start to dissolve. And so we want to clean these windows very quickly, and we want to put them back into a desiccator to keep them dry. Insoluble windows, such as barium fluoride or calcium fluoride, may not immediately react with aqueous solutions, but eventually they can fog and reduce throughput through the cell. So again, we want to be very careful what types of windows we're using with the type of sample that we have. If you suspect that you have water in your sample or that there might be moisture present, then you want to use different windows. And there's a large selection of those. I'm not going to go through all those here, but you can read up on those offline. Liquid sample cells, there's dispersive infrared instruments, have rectangular apertures, while Fourier transform infrared instruments require cells with circular apertures. And you don't want to mix the different types of cells for the different instruments. Sealed liquid cells have a fixed pad length, and the cell assembly is generally glued or epoxied together. The fixed path length makes them ideal for quantitative analysis. Demountable liquid cells means you can take them apart and put them back together again, and they're usually easier to clean as a result. We can use them for qualitative analysis as well as quantitative analysis because we have a variety of spacers that can be used to change the cell path length. We just want to make sure we use the same spacer time after time. There's numerous window materials that can be used, and we should only use water-soluble windows with organic solvents and samples, because any contact with water will start to significantly decrease spectral quality because of fogging of the windows. Water-insoluble windows are useful for almost any liquid sample, but there can be restrictions in the spectral range. So this was the slide I was thinking about. Here's the salt windows, and you can see the range from 40,000 to 33,000, somewhere in there, all the way down around 400, 650 in the case of sodium chloride. And we go to the water-insoluble windows. We have quartz, calcium fluoride, but see, we're starting to lose some sensitivity because, or spectral range, because of the cutoffs that occur in active areas of the infrared spectrum. So quartz, calcium fluoride, and barium fluoride are going to reduce the effectiveness of the technique because we're going to lose a good proportion or a good portion of the mid-infrared spectrum. KrS5 we want to be a little bit careful of because it's thallium bromide iodide, which is not very good for you. So you don't want to lick the window or something goofy like that. And they encourage you to have those polished professionally, or if they get bent or broken, to simply throw them out because they are not really good for you. You don't want to get exposed to thallium. Silver chloride and silver bromide are fairly frequently used, but they're also UV sensitive and they can darken if they're left in the sun. Zinc selenide and zinc sulfide are pretty good solid windows. They have good sensitivity, good throughput. They are a little bit fragile, but as you can see, the range of them is perfect for mid-infrared. And then there's an example of diamond. And we're going to talk about diamond a little bit later when we talk about some of the other accessories. So here, we're very concerned about the path length of the liquid cells, because as you can see, there's a very big difference. For instance, hexane here is in a 0.025 millimeter cell, and we get a very good spectrum. When we try and look at hexanol in a 0.015 millimeter cell, that's 15 microns thickness between the two windows, we see that we're over-absorbing. The OH and the CH stretches are way off scale, as well as the CH and OH bending modes. So we want to make that cell even thinner, usually on the order of 0.01 to 0.005, or 10 and 5 microns. So here's an example of a capillary film spectrum where we've just put a few drops of benzonitrile again between two salt windows. I can do that because I know benzonitrile is not going to attack the salt windows. And we get a very good spectrum. Again, The baseline near 100% transmission, and the strongest peak is right about 15% T. Excuse me. Another example here is isopropanol. Again, a few drops of the alcohol between the two windows, and we see a very good spectrum. Again, the baseline is near 100% T. The strongest peak is right about 20%, which is fine for this qualitative spectrum. We're not doing quantitative analysis here. So cast films is when we dissolve something like a polymer in a solvent, place the solution onto a cell window, and evaporate the solvent. Lots of different ways we can evaporate the solvent. One is by putting it in a hood, allowing the solvent to dry, or you can gently warm with a hot plate to promote evaporation, but on very low heat. Put a paper towel under the window to prevent rapid heating, and a sloping baseline or band distortion can indicate large particles in the casting or a sample that does not completely cover the sample beam. So here's an example of a cast film of resin dissolved in benzene, and we collect a spectrum of the solvent itself so we can make sure that if there are any interfering peaks marked with an X in this view, we know they belong to the benzene and not to the cast film of the resin. Another thin film sample here is polyethylene that was cast in the film, and it's approximately 0.5 millimeter thick. And you can see it's a little bit thicker than we really should have, because the bottom peaks for the bottom of the peaks for the C8 stretching modes are touching 0% transmission. But it still gives us a good quality spectrum. So now we've talked about transmission, we'll move on to the reflection techniques. Reflection techniques are what probably most people are familiar with. ATR, or attenuated total reflection, is that little device where you put your sample on the crystal, put pressure on it, and we collect a spectrum. Diffuse reflectance is looking at powders in a little sample cup. The powders are actually mixed with potassium bromide to give it kind of a medium background or a moderate background, and then we collect the spectrum. Regular reflection is, or specular reflection, is where we're doing an angle of incidence around 15 to 30 degrees, so that the angle of the incidence to the pink area on the sample is about 30 degrees. And grazing angle reflectance is where we change the angles of the incidence in collection so that we're just grazing the surface of the sample. And we use this at extremely thin layers, so we can actually use polarization sometimes to enhance our sensitivity. So each of these techniques has its place in the laboratory. We're going to go through them one by one. So reflectance accessories and methods are designed to provide analysis for capability for lots of samples that are difficult to prepare for transmission spectra, or for reliability or speed of collection, we use these accessories. So reflection accessories and methods provide analysis for powders, solids, and thick coatings that can be analyzed with diffuse reflectance. Flat surfaces and thin coatings can be analyzed using specular and grazing angle accessories, and multiple internal reflection accessories allow sampling of almost every existing sample type except gases, but we can do solids, powders, and liquids with an ATR and collect a very good spectrum. There's things we have to be aware of when we're collecting these spectra, using these accessories to collect spectra, and we've got to be careful on the interpretation of the data, because there can be some changes associated with the absorption spectrum compared to the transmission data. So while the standard transmission methods are widely recognized, sometimes it's actually impossible to prepare a sample for a collection using transmission. Reflectance methods often require little sample prep and can provide a universal sample interface. They're often simple to use, and in many cases, very easy to clean and maintain. And we have qualitative and limited quantitative analysis are routinely performed. The reason we say limited quantitative analysis is sometimes you don't have quite the range of sensitivity, the range of concentrations that you do when you do transmission sampling. Some disadvantages for reflectance: can often produce spectra that can require mathematical correction. And if you don't know that, you may not see the spectrum in the same way than if you did it by transmission. Can significantly reduce an instrument energy throughput and will often require more scans to get a good SNR value. We have to make sure that we have the optical alignment set up properly. And we'll talk about that as we go through this. And we need to check that on a regular basis. We often have limited sensitivity to minor component concentrations or extremely large concentrations. They can be more expensive compared to things like liquid cells or KBr pellets. Sometimes there's a limited spectral range, and we generally need to use them with Fourier transform infrared instruments, or FT-IR. So the first one we're going to talk about is diffuse reflectance, or drifts. Diffuse reflectance accessories focus the incoming beam, that first mirror in the picture here, in the figure, where it bounces up to a very large collection optic. And that collection optic is round and has a surface all the way around that sample cup so that the light coming off the surface of that sample cup is collected, then directed down to the last mirror in the assembly and onto the detector. We often run a blank using KBr or some other substrate, and we'll talk about some of those examples as we go through the rest of the presentation. Excuse me. So, specular reflectance. This is a diagram of what's actually occurring. So when the light comes into the sample, it hits the top surface of the sample, and it's bounced off right off the top of the surface. That's called specular reflectance. And often there's a block or a hole in that collection mirror to make sure that the specular component is automatically rejected. The other two beams, some of them are going through the sample, which is the little white particles. The KBr matrix is the black particles, and they're reflected or transmitted through the powder sample, the white, and then bounce off of some of the potassium bromide and are collected by the mirror and brought to the detector. Some of the light beams travel all the way down to the bottom of the cup and never to come back out again. So there's a lot of light losses here. When you compare the throughput of a drifts accessory to an instrument, the drifts accessory is only going to provide somewhere around 5 to 10% of the overall energy from the instrument as you compare before and after. So that's why we want to be careful with diffuse reflectance, because if we're looking at extremely low concentrations, it may not have the sensitivity to do so. And we'll have to collect a lot of scans, something like 128 or 256, to get a good spectrum of the sample. So here's an example of diffuse reflectance of a 1% phenacetin in potassium bromide. And again, you can see there's some drift in the baseline. We're not at 100%, and that's partially due to the loss of light as that light goes down to the bottom of the sample cup. We don't have it much stronger than that 20% value, 20% T value. So we've got a good spectrum overall. One of the things that's critical with diffuse reflectance is that we properly tune the sample cup every single time we collect a spectrum. So in this case, we're looking at the spectrum in the absorbance format with the peaks pointing up. These are interchangeable, percent T and absorbance. And in this case, what we want to do is make sure that there's often adjustments on mirrors or the height of the cup relative to the collection optic. And so what we want to do is tune the sample cup so that the spectrum of the sample is right down near zero absorbance. So when we convert it to percent transmission, it will look much like our standard spectrum with the 100%, the baseline at 100% transmission and the peak maximum at right around 20 to to 25% T. This is the correction that's used for diffuse reflectance, the Kubelka-Munk correction, or KM. It's a pretty complex equation, but pretty much every instrument software that I know has got the KM correction in its library of commands. And this is what happens when you do Kubelka-Munk. The first spectrum is before KM correction in the red trace. The second spectrum in the blue is after KM correction. And we can see how it sharpens up the bands, reduces the intensity a little bit, and basically corrects it for the differences that occur between diffuse reflectance and transmission. So diffuse reflectance, some alternative applications. We can do analysis of a rough or diffusely scattering surface. For example, the surface of tablets or pills can be roughened by using silicon carbide paper. That's basically wet dry sandpaper. That's what it's termed. It's 400 to 800 grit. And what we do is we rub the surface of the tablet so that we make the surface very rough. And then we put the sample in the drifts accessory. And some of the drifts accessories actually have a little holder for tablets and pills. Another way we can use diffuse reflectance is for thick coatings, such as paints or polymer finishes, by scraping the surface with that silicon carbide paper and then analyzing the surface of the paper. Infrared absorption occurs when the light strikes the surface, the particles on the paper surface. And what we do is we collect a background spectrum, from a clean silicon carbide paper or pad, and then we collect our sample spectrum. So there's a lot of these commercially available, and we can get the pads that are self-adhesive, so they have a little sample cup that has a flat surface, so the pad will stick right to the surface of that. So here's an example where we use silicon carbide or diamond pads, and basically we took a computer cover, which is a painted surface, as well as a cable connector. Some of this stuff is a little bit old, sorry. But like your USB cable, that surface is a polymer, and we've rubbed the surface and gotten some of the particles entrained on the pad surface, and then put the pad in the accessory to collect the spectrum. The same with the painted surface of the computer cover. So the next section is specular and reflection absorption and grazing angle analysis. These all use somewhat the same concept, where the sample is supported above two mirrors with one beam coming in, the infrared beam coming in to the first mirror, being bounced up to the surface of the sample. The light bounces right back down again to the second mirror and over to the detector. So in the case of specular reflectance with a very flat and shiny surface, we can do the incoming and outgoing infrared beams at about 30 degrees. So 30 to 35 degrees, where 90 degrees is parallel to the sample surface. Lots of polymer sheets, painted or coated metals, glasses or papers. Any flat coated surface is a possibility for specular reflectance. And we can also then go on to infrared reflection absorption is applied to coatings on flat shiny surfaces. So by widening the angle of that, so instead of 30 to 35, maybe 40, 45, 50 degrees, we start to widen out the angles and get more absorption from the surface area of the sample that then, as the light passes through the sample to the background or the substrate, as it's termed, which is very shiny, then it bounces back through the coating. And by changing that angle, we can go as thin as monolayer thicknesses. And by going to the grazing angle, about 80 to 85 degrees, we can simply graze the surface of the sample, but we increase the path length of the light as it goes through the sample. The Kramer's-Kronig transform is used to correct for the specular reflection. You can see that spectrum in the red is before the Kramer's-Kronig, and this is a polymethyl methacrylate sample. And you can see there's a lot of derivative bands in there. It looks pretty messy. But after we do the Kramer's-Kronig, we remove the imaginary specular component and calculate the real absorption spectrum, and you see a good spectrum for methyl methacrylate. This doesn't always work, but in the case of a coated surface, we did it on that as well. This was a coated paper collecting the sample with specular reflectance, and then after the KK transform, we get a very good looking spectrum in the %T format. Infrared reflection absorption. We have 3 different samples here where we have taken the sample which has a shiny substrate, and there's a polymer coating on the surface. And one of these is polymethyl methacrylate, as opposed to the other one that was a block of PMMA. This is actually a thin coating on a shiny substrate. Another example is silane, which is a silicon oil, and then polystyrene in the final spectrum at the bottom, where this is a thin coating on that shiny substrate, and we're basically setting up the accessory to collect the data from an incoming and outgoing angle of about 60 degrees. So as we change the collection angle and the incidence angle, go from normal to towards grazing, you can see how the intensity for that silane film gets stronger and stronger as we increase that angle all the way from 30 degrees to 75 degrees. And if we were to plot that, it would be almost a straight line. So the last section is multiple internal reflection, also known as MIR or ATR, attenuated total reflectance. So we're going to go into a little bit of theory here, sorry, but Snell's law predicts that at a critical angle, light energy penetrating a crystalline media with a refractive index greater than air will reflect radiation along the interior of the crystal. Excuse me. As the light beam strikes the interior surface of the crystal, an evanescent wave penetrates a defined depth into a sample that's in intimate contact with the crystal surface. So we see the sample in the blue pressed against the surface of the crystal in the yellow. And every time the light comes to the surface of that crystal, there's a little bit of light that goes into the sample, and we get an absorption process. And that's what we're trying to get, is that absorption process, so that we see in the final analysis a spectrum. Now, the MIR mechanism only provides a finite depth of penetration a finite penetration into the sample as it's in contact with the MIR element or crystal. For the majority of the MIR crystals, the depth of penetration is basically limited to 1 to 8 microns, depending upon the wavelength. So there's some things that we want to take away from this. One is that the depth of penetration changes as the wavelength changes. So as we go from 3,000 wave numbers at about 1 micron penetration down to 500 wave numbers, where most of the body of the information is located between 1,500 and 500, the depth of penetration now becomes greater and greater, all the way up to 8 microns. What happens is we get a change in intensity of the peak, the relative peak intensities, as we change the wavelength. So there's lots of different crystals used for MIR and ATR. Zinc selenide is the most common. KrS5 and germanium are some alternatives. We can also use diamond and silicon. There's lots of different configurations. Some have very specific sampling needs. There's multi-bounce crystals, things like that. Generally, multiple internal reflectance accessories, or MIR accessories, allow a sample to be placed on both sides of the internal reflection crystal, mounted vertically in the accessory. So it stands up, and we put sample on either side. HATR or ATR, horizontal attenuated total reflectance, usually present only a single horizontal surface, so we can only access one side of the crystal and get a sample analysis. Although the technique is referred to here as MIR, in practice, the terms ATR and MIR are often interchangeable. So here's a listing of the different crystal materials. And we're going to talk about diamond a little bit, because what we get is a change, or rather, we have areas of the spectrum where we're not supposed to get any light. And we'll talk about that in reference to a diamond ATR that was developed, and they're now readily available. And what happens is you can actually get data in that 2500 to 1600 area. You just have to be careful how you do it. But one of the things to note off this as well is the refractive index change from 2.4 for zinc selenide all the way up to 4.0 for germanium. Now, how is that relevant? Well, remember this. Oh, I don't have the equation. Sorry. So the point is that when we look at germanium, it has some unique advantages as compared to zinc selenide. And we'll talk about that in a later slide. But the point I wanted to make here is that the equation for the depth of penetration involves the refractive index as well as the wavelength of light that's involved with the MIR process. So we're talking about how the relative peak intensities are distorted compared to transmission spectra because the wavelength gets longer and the depth of penetration into the sample is greater. So what we see is for a polystyrene film sample, when we collect the ATR spectrum, the peaks at 3000 are really shortened. They're not very intense as compared to the transmission spectrum for the same sample. So we lose a lot of information if we're not careful, and we don't recognize that this process is occurring. But we can actually do a correction before the ATR correction and after the ATR correction to allow for the change in the depth of penetration as the wavelength changes in the spectrum. So what we're doing basically is we're enhancing the CH stretch region at 3000 and diminishing the CH bend and CH and the CC bends down below 1500. So this is important because if we're trying to compare an ATR spectrum to a transmission library, we will often get incorrect values for the hit quality index, or HQI, that we're looking for when we're doing a library search. So we've either got to collect the library or get the library in an ATR format if we're going to use an ATR sampling accessory, or we do the ATR correction after we collect the ATR spectrum and use the transmission library. But be aware that we may not get complete correction of the ATR or MIR spectrum when using that command in our software. So here we have a case where we're going to need to go to the germanium. So we have this carbon black filled polymer. Carbon black is extremely absorbing. And so with the greater depth of penetration for zinc selenide, we're actually getting too much absorption and it's distorting the spectrum. When we move to the germanium crystal, however, the depth of penetration is much, much shorter, on the order of about 0.5 microns to 2 microns. And so we get a much better spectrum that looks somewhat more like a transmission spectrum as we would collect it for that particular sample. So micro ATR accessories, especially diamond, can be used to examine lots of different types of samples because it's a small crystal element on the order of about 2 millimeters in diameter or a little bit larger. And we can use much higher pressures and get much better contact between the sample and the crystal surface. So this accessory is often sold with the instrument and termed a universal sampling accessory. So here's an example, of a methanol spectrum collected using the diamond ATR. And you can see we've lost no information here in that dead region from 1600 to 2500 that we saw in that one slide concerning spectral ranges. Another example is battery acid. Now, you wouldn't do battery acid on a regular sample window or ATR crystal because it would just eat it alive. But we can do it with diamond because diamond is pretty much impervious to any kind of sample, even the extremely low pH of battery acid on the order of 1 or 1.5, which ordinarily would eat every window up in seconds. The diamond is actually impervious to this, and we get a very good spectrum of the sample without any loss of data. And we clean the battery acid off, being careful not to touch it with our fingers, and we get a good spectrum, and we clean the accessory off and go on to other samples. Like this one, where we took some polyethylene terephthalate fibers from a vehicle, and we collected the spectrum using the diamond accessory. And we got a very nice clean spectrum of those fibers. Another example is nylon fibers. And this is the carpet from the same auto. And again, we just take a few fibers, place it onto the ATR accessories, put the clamp down to make sure that there's nice high pressure of the sample surface against the crystal surface, and we get a good spectrum. So, conclusions: transmission spectra provide the highest sensitivity and best detection levels for all infrared sampling techniques, but sometimes we require some extensive sample prep. Reflectance accessories can be the most expedient analysis method, but there may be some things we need to be aware of. It is important to always clean the accessories and tools immediately after analysis, and always verify the instrument and accessory performance before use to ensure the optimum results. Okay, and that's our last slide.
Thank you, Dr. Larsen, for that informative presentation. We will now start the Q&A portion of the webinar, and we'll address some of the most commonly asked questions by our viewers. If you have any questions you'd like to ask, please do so now. Just click on the Ask a Question drop-down box located on the far left of your presentation window. Type your question into the box that appears on your screen and click the Send button. Our speaker will follow up with your questions via email. So let's get started. Our first question is, does the ATR method of analysis have any disadvantages?
Thanks, Judy. Yeah, that's a good question because we kind of touched on it in the presentation. We just have to be very careful in comparing the data collected with the ATR to data collected from some other method. Now, if I compare one ATR spectrum to another ATR spectrum, we won't see a whole lot of difference there. But if we're trying to compare it to a diffuse reflectance or a transmission spectrum, we may see some differences in the relative intensity peak values, and that could be a little bit confusing. Also, there can be some slight peak shifts using the ATR technique. And again, as long as you're aware of those things, you should be fine going forward.
Thank you. Oh, were you done with that one?
Yes.
Great. Okay, your next one is, how do I verify the performance of the accessory or analysis method used?
A lot of times what we'll do is we'll take some standard sample that we know what the results should be. We run that sample using the accessory or the analysis method and make sure that we're getting the proper data. If we don't see the valid data that we're expecting, then we need to investigate whether the accessory is faulty, like say it's not properly aligned, maybe it's not tuned properly, maybe our potassium bromide for diffuse reflectance is wet, or perhaps for a KBr pellet, it's wet. We need to look at those things before we start running regular samples. And a lot of times these checks are just a few, maybe a minute or two before we start collecting data for the day. We just want to know from that point forward, going on, that the data we're collecting with the method or with the accessory is going to be valid, that it's good, that we've got everything in tune the way we should have.
Thank you. Okay, next one is, do you recommend any particular analysis method?
Oh boy, that's a tricky one. Excuse me. A lot of it depends on what you're trying to do. I mean, for qualitative analysis where I just need to know what the material is, the ATR accessory is probably the easiest, most versatile method and accessory to do this. But if I'm trying to do quantitative analysis and I'm trying to do a very wide range of quantitation, we might want to go to one of the transmission methods because it's going to have a lot more flexibility for quantitative analysis and can accommodate a much wider detection range than, say, the ATR method or some of the other reflectance methods. The other side of that is let's say that my sample is something that's very shiny, has a very thin surface or very thin coating on a shiny surface. Well, then ATR or transmission is not going to work. So we have to evaluate what the sample is and what the final answer we're trying to obtain. And that will help make some decisions as far as what accessory, what method we should use.
Thank you for that. Looks like we have time for one more question. How do I verify the instrument performance for the accessory or analysis method?
That's kind of similar to the one I talked about earlier, but it's very similar. A lot of times we remove the accessory from the bench, from the instrument, and we make sure that the instrument's working properly. A lot of times we can monitor the energy or the interferogram energy. There's ways to do that in your instrument, and a lot of times we just have to dig out the manual and look at that. But I really do recommend that every single morning or every day that we use the instrument, you don't know what the last person did with the instrument, so you just want to make sure that it's performing the way you want it to. Then you put the accessory in, make sure it's getting the same data or the same energy value that you got last time, because you're going to write all this down in your notebook. And that way, you know, when you use the instrument, it's working to your satisfaction and you've got the data and the information. So if somebody ever questions the results that you've obtained, you say, look, I verified in the morning or in that day that the data I'm going to get from this accessory or this instrument is going to perform like it did the last time I used it, because I'm looking at the values in my notebook and I'm getting the same information time after time after time. That's your reassurance that you're getting complete, quality, optimum data every time you use the instrument.
Thank you. I would like to once again thank Dr. Larsen for his presentation. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through January 25th, 2019. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's event. That is all for now. Thank you for joining us. We hope to see you again soon. Goodbye.
Bye.